Hi guys, it's your guy Olumide. Today we'll be talking about a powerful data structure called the tries. Tries, also known as prefix tree, are specialized data structure that are tree-like in nature, meaning that they consist of nodes with values and edges that connect these nodes together. And what a trie does is that it efficiently stores string by taking advantage of sheer prefix. So to understand how a trie works, let's consider this string internet. We can store this string as a sequence of connected nodes where each node represents each character in the string. So you see, this particular node represents value I, then N, then T, then E, then R, and so on like that. Let's say we also want to store the word interface. Now, instead of creating a separate sequence of nodes for interface, we take advantage of their common prefix inter, because internet starts with inter and interface also starts with inter. So we take advantage of this common prefix, and both words can share the common prefix inter, and then the remainder of the word that are not the same can branch out from the end this R. So because inter consists of INTER and up to IN up to R, in both cases actually are the same, and so from the point R onward they will now share different sequence of nodes. So for instance, for interface now it is FACE, but for internet it is NET. So at this point R, so they are gonna share NET and FACE. By allowing words to reuse existing nodes based on shared prefixes, trees efficiently prevent redundancy in string. So having to write the same set of words again and again is reduced by using tree or tries. You can call it, sometimes I call it trees, but I think it should be tries. There are two attributes that each trie node should have. I mean, for any trie node that we'll be using, they should have two attributes. The first one is the children. Each trie node should have a data structure to store reference to its children, that is its child nodes. And what we simply mean by this is that this particular trie node I, so you know it's a node, right? So this trie node I or let me say this trie node with the value I or string character I have a child which is N. N also have a child which is T. T has a child which is E. E has a child which is R. Now you see that R have two children, right? It has children N and F that branches out from R. While N have one, E have one, then the rest have one. F2 have one, A have one, C have one, E have one. So that's what we call children of a trie node. Most times we use hash map to represent the children, like the data structure to store these children for each trie node. And so the hash map, we have the particular string A, for instance, now will be the string A will be the key in the hash map, while the child node itself will be the value of the key in the hash map. Sometimes an array is also used if the possible characters in the tries, the possible characters that are going to be in the tries, if they are already known, if they are limited, so we can use an array instead of an hash map. So it will be an array of fixed length. For example, if they only contain lowercase English letter, we just have to use an array of 26 of size 26 to represent these possible characters in the trie. So that way we'll be able to keep track of the children at each, or possible children at each node of each node as well. And the second characteristics or attribute of a trie node is actually the end of word character, so which is actually a Boolean attribute. So it's going to be an is word, so to confirm if the node is the end of a word. So each node will have its word attribute, which actually specify the end of the word, that okay, if that particular, it will be set to false by default. But if that particular word, say talk of internet now, you see that T is the end of the word. So the for everyone else, its word attribute will be set to false, but for T it will be set to true. So it's used to identify if that node is the end of the word. So sometimes to represent the end of a word indicator, we also use a string variable like word. So instead of using a boolean attribute, we use a string variable that actually store the word itself at the node. So it's not just gonna store if true or false, if it is the word or not. It's gonna store the word itself. So this is usually used if we also want to know the specific word that end at this particular node. So these are two major attributes of a trie node. Now let's talk about the tree structure. So we are going to be considering a trie now. So it's down here, so it's quite long. So we are considering that trie. It has been populated by inserting the word, this set of words: internet, interface, bytes, dog, and dig. So these are the words that are inserted into the trie, that has been populated in the trie. Every word that is represented in the trie, in this particular structure now, actually branches out from the root trie node, which actually does not represent any it actually does not represent any character. So it's just the root where everything else branches out from. So consider this internet now, that later branch out to interface, and this inter shared node or shared prefix that later branch out to interface and internet. Yeah, you see that it all emerged from the root. And one thing you will notice is that, imagine if you want to bring in a new word like egg into this particular trie structure now, it's gonna cause a new branch to form. Why? Because it can't go with this, because this is not starting with E. It can't go with this is starting with B not E. It can't go with this because this is starting with D not E. So we need a root node whereby every other node will branch from, even if they are shared or not shared. For instance, if we consider egg, fine, we're gonna be having a new branch from the root node. So, and that's why we need the root node. So the root node necessarily does not actually represent any character at all. It's just like the reference, a base case for where all the other words that we are going to be populating into the tree we branch out from. You will notice this is word equals to true. So at the end of each branch, or let me say at the end of each word in the tree, look at this now. You see that dog, this is dog, and then at this particular last node G, we set its word to true to signify that this is the end of a word. So right, because actually, imagine we are giving dog and as well as dogs, right? They are as two different strings that want to populate into the hash map. So we want to set dog to its word equals to true, because that is the end of a particular word that was given to us. And then at the same time, this is going to extend, right? It's going to extend like this, something like this. So it's going to extend something like this. We're going to be having the S here, right? And at the same time also we want to set this particular one also to its word equals to true, so that by the time we start to search for probably want to do a search for the word dog or for the word dogs, so we are going to be sure that both dog and dogs exist, and this is not just a single word dog or dogs, right? So both the node, this particular node with character G will be set, we have this word set to true, as well as S, we have this word set to true, so that we can know that both dog and dogs are valid word in our trie structure, and not just a single word dogs. So that's the essence of adding the is word attribute. So let's look into the time complexity breakdown for trie operation involving a word of length k, right? So why? Because in trie it actually deal with string, trying to populate string, adding this number, adding this length of string, adding another one. So that's what tries actually does. So let's consider a word of length k. To insert it into the trie we take OK time. So and it insert a word into the tree, and what OK does means that actually it actually take the whole length of the word. So it's just like ON, it takes a linear time to insert. Why? Because it has to insert it character by character. Okay, let's consider the slash operation also works in OK time, because it also has to do it character by character. So because whenever one perform a search each and every word, or each and every character in that word that are trying to search, is going to search into the tree node for it. Search prefix is also going to search OK, provided the prefix, probably you want to search the prefix inter, so it's going to search through each character in that word inter. So and what it does is that it check if any word in the tree starts with a given prefix. So you should know that the difference between the search and the search prefix is that we can just decide to search prefix of do or by, not necessarily the whole word bytes, right? So once we can get b and y in our tree structure, we return true. But if it is a search, a real search, we are gonna after searching through, we're gonna check if that node, the last node that we should search, if it is a word, that is if there is word property is true. So that means that fine, that is the end of a word and is a valid word. But for prefix, we just want to know if there's any branch in the tree that actually begin with those words. So that's what prefix does. So delete also, if you want to delete out of the tree, is going to take OK time, whereby it's keep on deleting each and every node that is contained in that word that you're trying to delete. Probably you want to delete inter now, it's going to go and delete I, then N, then T, then E, then R. So delete the word from a tree. So now let's talk about the reward application of the try data structure. So when you start typing a word, you see that some system use the try to quickly suggest possible completion, right? Probably you are using some application like word web application. You see that or even probably are searching, yes, or let me say you are typing on the internet using your keyboard. You see there is autocomplete option, whereby when you start to type, some system use a try to quickly suggest possible completion. So each node in the try actually represents a character, and as you type a particular character, the system is going to traverse a try based on that input character. So this allows the system to efficiently retrieve all possible words or phrases that start with the entered prefix, enabling fast autocomplete suggestion for us. So that's it, and we are going to be considering some problems that are related to tries in the subsequent videos. Do well to follow us really on YouTube. That's important, because most of our videos might be quite lengthy, because I have to do the code implementation and then the logic, and then I have to write it out in code, and I want to do it in a very simplified way that you won't have a problem understanding and grasping. So most of the time the complete video is always on my YouTube channel, so do well to click on the link to my YouTube channel if you are not watching this through YouTube, and subscribe to my channel, because there's more videos, more DSA problems that we are going to be solving together. More is coming, and you don't want to miss it. Thank you.